Then really epsilon. There is a C such that if I look, so I have these heights in the like X, Q, H, then yeah, so it looks like.
Hello, can you hear us on Zoom? No, they're not hearing us.
Yes, we can now. Thank you.
Yes, we can hear. Thank you.
Yes, just started.
Yes,
Thank you very much.
I can hear you now.
Okay.
So I have these heights in the like X, and we change them up. Yes. Well, that's not very difficult. So we don't say. Okay, so. Is something I should carry on? Yeah. Okay, so I'm going to have X, Q, H for the points in X, the rational and bidimensional. Okay, so it's all X I'm going to see. So it's going to take the number of points of X, applied to most H, the little part, and that's supposed to C times X. So the number of possible points is like 8 to the 2n, and so this is way forward. And in fact, in this generality, what you have an overall structure and anything more about, you can't really improve this stuff. You can count more stuff, so you can count, say, points of bounded degree over Q. You can count other more complicated things. But the basic H difference it can't be improved in general. Okay, so this theorem has had many applications, most of which rely on the definability result, which we're going to say again. And in these applications, you get the finiteness of something. In the simplest cases, you get the finiteness of the set of algebraic numbers. And you'd like to be able to compute that finiteness. You'd like to say these are exactly the numbers that solve the equation. And for that, you need to be able to compute this C here in terms of epsilon and some kind of description of X. Now, in the general minimal setting, not clear what we would mean by some kind of description of X. Right? I think my only structure could just be the real field with X. Right? But in a kind of more concrete setting, then we have a notion of kind of complexity with the final set. And that's what I'll talk about. So even in something like R, where you have like functions, you need to associate something to the analytic functions that you could use to talk about complexity. It's not some kind of measure of complexity about a function, like a radius of convergence, like a radius bigger than the radius of convergence. Anyway, I'm going to work with tracking functions, so I'll give you that function. So suppose I have F1 up to FL analytic functions. On U, and U will always be a product. So it's a subset of R to the N, and it's a product of both of them. Okay, then this is called a pfaffian chain if the derivatives that you go along depend polynomially on the functions you already have. FL is a pfaffian chain. There are polynomials. Pij in R x1 xn and y1 up to y I. So I goes from 1 up to L, J goes 1 up to N. Such that when I differentiate Fi with respect to x j, that is Pij of x 1 up to I. So for instance, X is a pfaffian chain of length 1. Log moves in a chain of length 2. But then the usual equations for sine and cos each depends on the other, so you don't have this kind of shape. So that doesn't mean that they're not pfaffian, so they're not. So if I had a pfaffian chain with a normal structure, I get a normal structure. So that's the theorem of pfaffians. So that means sine and cos can't be pfaffian. Okay, so that's a pfaffian chain, and then a function. It's pfaffian with this given chain. If F is given by a polynomial in this chain. X is X. F1 L. So some and now we've got, if I have this, I've got a way of measuring its complexity. I've got all these numbers I can use. So we'll define the format. Okay. To be the sum of the number of variables, the length of the chain, and the degrees of all these polynomials. So that's n plus L plus the degrees of Pij. We'll define the degree of that. To be the degree of this polynomial here. And we'll see later why we want to do this one second. Okay, so then if I have a pfaffian chain, I can define semi-pfaffian sets. So X is semi-pfaffian. I think it's given by some zeros of some pfaffian functions and positivities of others. So I have a bunch of pfaffian functions by making zero, and then I have another bunch by making positive. So this is semi-pfaffian. So here all the G1 is the Gn or H1 up to Hn, they are pfaffian with some common chain. So if they have different chains, you could just put the chains together and make long. And then the format of this X is going to be the maximum of the formats of all these functions. And the degree is the sum of the degrees. So the degree also codes the number of function values. Pardon? That's right. So this is basically the format and degree of this representation. So you look at the small format. No, you just work with a given representation. And then subfactor is going to be projectionalism. And I can define its format and degree if you know them. Okay, and then the theorem. So this is joint work with Binyamini, Schmidt, Thomas, and the year is still completely valid. And it's an effective Pila-Wilkie for submapping. So with a sector control over it. So here it is. So for all A and x of 0, there exists effective C and gamma with the following. So suppose X is subpfaffian with formats opposed to A degree minus B. Then eventually is 1. The number of points on the transcendental bar. I think that's the way to C times D to the gamma times H to the X.
Yeah, you don't want U to be too complicated.
So I'd say somewhere,
Oh.
the product of that.
Oh, sorry.
That's right. If U was unpleasant,
Yeah,
then that will be captured by the function.
U is used quite a lot of that. But Y and U, thanks.
Oh, sorry, one.
Yeah.
Oh, sorry, two.
Yeah.
So that is the Bible. Yeah, value is the same stuff. Okay, so this is theorem, and so like this here, the C times D to the gamma is the C that you're looking for. So we agree that it's effective, but also it depends polynomially on this degree. So this is the degree of and that in applications will correspond to the degree of the right. We'll see that today. So that's all you get for sub-mapping sets. And then there's another result, which I'll perhaps just say. So if you take R back, the expansion of the real field by all pfaffian functions, and you put a viable set there, then we get an effective C, where it's effective in epsilon and the complexity of the formula. So in R back, we don't know multiple things. So we don't know that every set is sub-pfaffian. So you have to have a more complicated formula possibly. And in that setting, we don't get this here. We just get an effectively induced. But this is the one I'll use. So, okay, I'm not really going to talk about the proof. I'll just say some things. Well, okay, so first, the last. So one, you can do better here. So Gal will talk about this, I think, on Thursday. So the C, D, epsilon can be improved to C, E to the gamma log H to the L. So this here can be replaced with a log H. So this you do the Binyamini. And I think Gal will talk about this on Thursday. Alternatively, I will talk about this tutorial next week. But actually, what assumption? So in this theorem, there's just a literal improvement on this theorem.
No.
It's a number. It depends. I mean, there's C, gamma, and L. No, you see, like, so it's true, they go to the restricted pfaffian, but it's all uniform in the restriction you make. So in this case, when you're extending the Bible, it's just like you get to 12x, you get something. Okay, yeah, so Gal will talk about this on Thursday, and I'll talk about it next week. Actually, this kind of help doesn't help with some applications. It helps a lot with other applications. So I'll give one of those next week. But for the ones I talk about today, this actually doesn't make a difference. So we might two. That's my one. So the proof, we prove it by proving something from restricted sub-pfaffian sets. So they do form something. And the point is everything is uniform in the restricted you take, so you go into unrestricted points too. So what are the ingredients for the proof? So there's lots of results from effective pfaffian geometry that we use. So the most basic is the following. If you have a pfaffian function, and you look at its zero set, so this is pfaffian. Then its zero set, as opposed C times B to the gamma connected components, where C and gamma depend on the format of X, and B is the degree. So this is a theorem of Pila-Wilkie. And this has played a very important role in reliability generally. And in particular, at least so you see it down effective, very explicit. And this is kind of at the heart of everything we rely on, but actually we need much more than that. So we need results of Gabriel and Borobio, now, when in the Pila-Wilkie group, most of the work is in parameterization results, and then there's putting that with what things we already know in some of it. And it's the same for us. So most of what we do in the restricted setting is parameterization result. And we can't just like plug in these effective things into the Pila-Wilkie group because they use compactness, but more also because the structure of their group wouldn't use what I think these kind of factors. So instead we follow a different approach to parameterization, which is not me. And that's what lets us get this here. So in the Binyamini group, there's a step where you massively increase the number of variables. And that would make this go wrong. And the compactness is not so hard to get to that. You put everything in parameters from the beginning. Okay, so if we want to apply this, we need lots of functions which we know have definitions in terms of packing functions and which are useful for applications. So I think we might hear more about that on Thursday too, but I'm going to work with the functions. Yeah. Actually, maybe this way both. Okay. So, yeah, so to apply this, so we don't expect to say the most famous applications of the Binyamini theorem are to the unreal conjecture, which in the basic case uses the J function. Now we don't expect to be able to use this for the J function, but we can use it in other contexts. So, okay, so suppose P is an elliptic curve, as we see. So I'll talk more about this next week. If you don't know what it is, you can think of it as given by y squared equals 4 x cubed minus g2 x minus g3. The g2 and g3 some complex numbers, such that this qubit here has a sequence. Okay, so if I have such a curve, it's isomorphic to the complex number divided by the lattice. So the lattice is a discrete subgroup of C rank 2. And it's via as P functions. So it's exponential, which sends Z to P of Z, P prime of Z. Now, where this is something called the divided by P function, I won't write down the series for really matter. So this function is periodic, so it's not going to be definable on C, but if you restrict to a fundamental domain, it's restricted analytic. It's almost that's all whole. But so then it's in our rank. Now, what we need is something pfaffian. And then there's a theorem which I proved with Schmidt. Published in 2020. So it says there are well explicit C and D with the following quantity. So suppose the elliptic curve and the lattice up above, and suppose further that we have fixed generators omega 1 and omega 2 generators are the lattice such that the ratio omega 2 over omega 1 lies in a standard choice of fundamental domain. So given any lattice, you can do this, the generators always exist. And then put omega, so this is going to be a fundamental domain for this exponential B1 omega 1 plus B2 omega 2. So B1 and B2 are in 0, 1, and then not at 0. And if you do this, then when I look at the graph of this exponential, and I restrict it to this fundamental domain, that's a sub-pfaffian set of format at most C and degree at most D. Sub-pfaffian format equal to C and degree less than or equal to D. So if I just wanted the existence of C and D without knowing anything about them, this would follow from Kobe and Sergei's definability result for the two variable P function, where you like the lattice is also a variable. But I don't know how to use that to get actual values of C or even to prove grouping actual values. If you don't want the uniformity, so if you just work with a fixed lattice, then this kind of definition is the result of lattices. But to combine the two was what would work. And this is so I haven't written them down because we wrote it down in a slightly different technique and you have to make some computations to get it just I haven't got that. Okay, so this gives us some functions that we can apply this to. And so what we apply it to is Mann and Mumford. Now, so this makes kind of, so we use what's called the Pila-Wilkie strategy, which I'll talk about in my tutorial next week. And these two things together make the counting part of the Pila-Wilkie strategy completely uniform for products of curves. Unfortunately, there's an arithmetic degree of two, which is not uniform. So you lose the uniformity of the lattice in the arithmetic. However, it is uniform in certain cases, if you restrict P of it. So that's what we'll do. So, certain arithmetic curves are special, but they have more isomorphism than normal. Definition. P has complex multiplication. Right, let's see there. If it has more ring is, I mean, always contains set, if it's strictly bigger, we say it has complex multiplication. And then we have the following theorem. So this is a special case of a result through the Gal. So it's in 2016, I think. This is, I'm going to state it as a special case. So take G is 1. And then for theta less than 1, there's an effective C bigger than 0 with the following. So suppose D has complex multiplication. And for A, D to the G. And then take a torsion point on A, whose order is exactly N. Sorry, I also need D given my equation like this, a diagram equation. Over the rational doing the J variably. So this is a bit more clear definition. And then the statement is if P is on A, if that's order N, then its degree over K is large. Polynomially large, if it were. And the point here is that this C doesn't depend on it. So it's uniform, assuming complex multiplication, which is a very special assumption.
A.
Sorry?
What is capital A?
A is E to the G.
Oh.
So this also, I mean, this works for general C and B, right? Okay, so then you put this with that and this. You do the Pila-Wilkie strategy and you get what I'll write down now. Sorry? Yeah, like a primitive point order. Right, so yeah. And we're looking at that thing will take longer as well. So if you haven't seen it before and you're coming next week, you'll see the Pila-Wilkie strategy. So I'm not going to give it now. But it's very cool if you haven't seen it. So you should come next week. Or maybe it's too late to register. Okay, so that's, I think this statement here is false without fear. So what's expected, I believe, is that if you replace this K here with Q, you have something like this. What's known is a uniform lower bound, but it's much, much smaller than. I'm not sure how. Okay, so what do we prove? Theorem. So this is with now. Okay, so let G be 1. There are effective C and M. The following property, suppose I have E, A, and K having Gauss equation. And suppose L is another field extending K. And B is irreducible subvariety of A, so AB to the G, and B is defined over L. Now, let's suppose also that B doesn't contain a translating elliptic curve by torsion. So if it did, it would have lots of torsion points to make all we want. But suppose it doesn't, then if I have a torsion point on B, of order N, right, exact order N, we have N is bounded by C times the degree of L over K times the degree of B, N. So this is a uniform band on the order of a torsion point, assuming CL. So there have been other uniform band results recently without assuming the product of elliptic curves or assuming non-multiplication. So, for instance, there's one due to beautiful Gareth and another one due to Pila. But in those, what you found is the number of torsion points. And if you want to turn that into a round on order, you lose uniformity, which is the height of the environment. So this gives a uniform bound, kind of gives a more uniform computation before. So I have like 3 minutes left. So okay, I'll just say. So using this, we can create an effective version of the theorem concerning subvarieties of final products of the Dolder family. And what's nice is so we don't use the Binyamini method. We use this is really uniform instead, because if you have the Dodder family, you don't expect pfaffian definitions, so we don't expect your Cuba counting. But this is so uniform that we get something there too. But I won't write that out, I'll just stop. Thanks.